We'll take a small example to do the stability analysis of abutments. So here is a question that is given. We need to verify the stability of the abutment shown in the figure, and the details are given here. The material of the abutment made is concrete. Density of soil is given as 18 kilonewton per meter cube. Span of the bridge is 15 meters. Coefficient of friction is 0.6, that is mu. Angle of friction between soil and concrete is 18 degrees. Angle of repose of the soil, that is angle phi, is equal to 30 degrees. Live load on the bridge is mentioned as IRC class AA tract. The diagram is already given here. The details are also mentioned. So the base of the abutment is already fixed. It is 1.2 plus 1.4 plus 1.2, that is equal to 3.8. The top width is 0.6 and 0.8 at certain heights. The total height of the abutment is mentioned as 105.00 meters. The next level is 103.20 meters, and the base of the abutment is 100 meters. So the bridge deck consists of 3 longitudinal girders of 1.4 meters depth with a deck slab of 200 mm depth. We will need this particular data to calculate the self weight of the structure. So to continue, the first step is to calculate the self weight of the abutment. The same diagram I have redrawn here, giving all the details, which will be easier for us to calculate the self weight of the abutment. So to get the self weight, I have taken 24 as a density of concrete. Then it will be equal to 24 into area of section 1 plus 2 plus 3 plus 4. I have divided this entire abutment into 4 sections, as it will be easy for us to calculate the area. So it will be the first section, it is half base into height, as it's a triangle. So it is half into 1.2 is the base and 5 meters is the height. We got this 5 meters with the details that is given in the problem itself, that is top level is 105.00 meters and the bottom level is 100. So 105 minus 100 gives you 5 meters. I have shown the calculation in the diagram. Similarly, we have got height 3.2 from the previous diagram. So it is 103.2 minus 100. So coming back to self weight, it will be equal to 24 into area of first triangle plus area of the rectangle, that is section 2, plus area of rectangle, that is section 3, plus area of triangle, that is section 4. This gives me a total value of 251.52 kilonewton. The second step is to calculate the dead load from the superstructure that comes on the abutment. Now here, span of the bridge is mentioned as 15 meters. 3 girders of 1.4 meters depth. Width of the girder is given, should be taken as 0.3 meters. Deck slab of 200 mm depth. Width of the deck is equal to 8.7 meters. It is considered. Wearing coat thickness is 80 mm. Again, we have assumed this, and unit weight of wearing coat is usually taken as 22 kilonewton per meter cube. So dead load of the girder will be equal to width into depth into length into number of girders into 24, that is the density of concrete. So width is 0.3, depth is 1.4 and the length of the girder is 15 meters. We have 3 girders, so multiplied by 3 and multiplied by 24, which is total equal to 453.6 kilonewton. This is of the girder. Next is dead load of the deck slab. Now, when I say deck slab, it is the deck slab that is constructed with concrete. Also, the wearing coat load also will come in this particular criteria, that is dead load of deck slab. So, it is 24 times D of the deck slab plus 22 times D of the wearing coat into length and width of the bridge, total area, which is equal to 24 into 0.2. 0.2 is the depth of the deck slab, which is given, plus 22 into 0.08, that is 80 mm thickness of the wearing coat, multiplied by 8.7 into 15. 8.7 into 15 is the area of the entire bridge, 8.7 is the width and 15 is the span of the bridge, which is equal to 856.08 kilonewton. Now the total dead load is equal to dead load of the girder plus dead load of the deck slab. So, which is equal to 1309.68 kilonewtons. Therefore, dead load per abutment will be divided by 2. as we have two abutments on two sides of the bridge, half the load will be taken by one abutment and half the load will be by the other abutment. That's the reason we divide this total load by 2, which is equal to 654.84 kilonewton. Dead load of per meter run of abutment will be divided by 8.7. Now we need to calculate this for every meter, so we divide it by the width of the bridge, because the abutment will be for the entire width of the bridge, which is equal to which is taken as 8.7. So it is 654.84 divided by 8.7, which is equal to 75.26 kilonewton.